All right. Good morning, folks. Let's go ahead and let's get started. Today, we're going to go ahead and we're going to start chapter 15, and we're going to talk about buffered solutions and try to get. Oh, no, I'm sorry. Let me go ahead and let me start my timer here. That'll keep me honest and on track here. Okay. So we will start chapter 15 today. Please make sure you understand then that with the material that we covered yesterday in class, when we were analyzing the structure of the different molecules to determine whether the molecule will have acidic properties or basic properties. Please make sure you can do those basic structural analysis. Um, Even though we're not spending that much time on it now, structural analysis is incredibly important. It is incredibly important. We'll be revisiting the topic again. We'll be dealing with it again later on in this course. But it becomes a huge skill that you have. It becomes hugely important. It's a very important skill that you'll have to be able to learn to do well in your later chemistry classes. And so when you're off and you're taking organic chemistry or you're doing biochemistry, and it basically most of it is all about structural analysis, looking at the properties of molecules, looking at the properties of macromolecules based upon the structure of certain parts of those molecules. It is very important in determining the function of those molecules. So structural analysis is very important in helping us to understand how a particular molecule will function. And so as you go on, there are areas of study completely devoted to studying structure and how structure is responsible for function. Bioinformatics is it's a burgeoning field that I think that many of you, if you have not looked into or have not thought about, please come by and talk to me about it, because it's a very interesting field, especially for those of you folks who have an interest in computers as well. We see that in bioinformatics, a merger of what the properties of biology and biochemistry merged together with programming and computer and data analysis. So come by and see me. I did a little bit of research. My research a little bit had to do with bioinformatics, and so come by and see me. And I think if you're interested in genomics, if you're interested in proteomics and how structure is important, come by and see me, and we can talk about it. Okay? But structural analysis is very important. Okay? But again, like we did not spend much time on it. So please make sure you practice it. Come by and see me. So I think I had posted for you, I think set F and set G from chapter 14 to give you a little bit more practice with it. So come by and see me today if you want to, but stop by tomorrow. I'll be available tomorrow after my 7th period class. I'm sorry, tomorrow I have a meeting after my 7th period class. On Friday, if you want to stop by on Friday, we can go over the structural analysis a little bit more. Okay? And the analysis we did was on a very basic level. But also remember, structural analysis, the last part of chapter 14 will be on the next exam. So please make sure you keep that in mind. Okay? But we do have to move forward. We do have to move forward, and we do need to start chapter 15 today. So let me go ahead then. Let me share the screen with you. And let's go ahead and let's take a look at what we will be dealing with here in chapter 15. So in chapter 15, then, we basically bring to a closure our study of acid bases. And we're going to use our understanding of acid-base equilibrium to examine then a solution, a type of solution that that is very common, that is actually very important, not only in chemistry but also in everyday life, in us, for example. Okay? And that is, we're going to focus our attention in this particular chapter. We're going to use our knowledge of acid-base equilibrium, okay? And also we're going to pull on our knowledge of stoichiometry, which we learned way back in chapter 4 at the beginning of this course. We're going to use both of those to understand then how buffer solutions work. Okay? And so let me start out by introducing to you what a buffer solution is. A buffer solution is a solution that's made up of an acid and its conjugate base, or a base and its conjugate acid. So you got to make sure you remember the terms that we talked about: conjugate base and conjugate acids. We talked about that, and I'll review that with you here in just a moment. But that's what a buffer solution is. A buffer solution is a solution in which you're mixing together two other types of compounds, two other types of solutions. And the idea behind the buffer solution, as the name implies, is that, excuse me, it can provide a buffer to any changes to the pH of a solution. Okay? And so organisms, we living organisms, are dependent on making sure then that our pH falls within a very, very narrow range. That if our pH shifts beyond that range, then we're in trouble. The pH is typically for humans, for us at least, the pH is going to be roughly about 7, a little bit over 7.5, around 7, neutrality. Okay? And so the blood pH has to be around 7.4. And so what our body does, one of the buffer systems that our body uses is a carbonic acid, okay, bicarbonate buffering system. Now, what is what is this particular buffering system? Well, what we have in our blood then, if you notice here, what we have in our blood then is both the, oops, let me go ahead and do this here, both the bicarbonate, okay, we have the carbonic acid, which is what we have right here, CH2, H2, CO3. So this is the acid. Okay. Now remember, when this acid breaks down, and carbonic acid is a weak acid, and so we know then that when weak acids break down, the equilibrium is going to highly favor the undissociated form, okay, as opposed to the dissociated form. But when it does dissociate, okay, what we get then is the hydrogen ion. Okay. So when carbonic acid dissociates, we get the hydrogen ion and this anion right here. This anion right here is your conjugate base. So this is the acid. Okay. Okay. This is going to be the conjugate acid, and this is going to be your conjugate base. So this is the conjugate base of the carbonic acid. And this particular ion right here, this particular ion here is what we refer to as the bicarbonate. Okay. And this is, I'm sorry, let me go ahead and do this here. A little bit here. Okay. This is what we refer to as the bicarbonate ion. Okay. All right. So we see this bicarbonate, sodium bicarbonate, for example, is baking soda. We see a sodium. We see this bicarbonate ion in common usage. But our body takes advantage not of the carbonic acid. It doesn't take advantage of only this right here. What we see happening then is our body takes advantage of a sodium bicarbonate and a mixture of sodium bicarbonate and carbonic acid together. So if you take a look at this here, there we have the bicarbonate ion right here, and there we have the carbonic acid right there. And so what the body does is it has both of these. Now it introduces, so the carbonic acid there, but it introduces this bicarbonate in, let's say, in the form of an anion or an ionic compound, a salt, and we talked about salts at the end of chapter 14. So what happens then is we can introduce the bicarbonate ion in here in the form of, say, sodium bicarbonate. Now, the body doesn't quite do this, and I'm not a physiologist. I'm not familiar with this. You may want to check with either Mr. Dunn or Miss Ray to ask them, how does the body introduce in this bicarbonate ion? But the idea then is that we can make a solution then of this particular buffer here, this bicarbonate carbonic acid buffer. We can make this buffer solution here. So this is a solution here by adding carbonic acid and adding to that sodium bicarbonate, adding that in. The idea then is that the sodium doesn't do anything. Remember, sodium doesn't do anything, but the bicarbonate, that's what we want. Okay? Because what does the bicarbonate ion do? We're going to learn about that in this chapter. So the combination of both the carbonic acid and the bicarbonate ion, that is what we refer to as a buffer solution. Okay? A buffer solution is simply a solution in which you have an acid and its conjugate base, or base and its conjugate acid. And again, these buffers are very important, not only in chemistry, but in maintaining everyday life in most organisms. Okay? All right, so let me go ahead and save that, and let's examine then what these buffer solutions do. Okay, so let's take a look at the chemistry of these buffer solutions. All right, to start out with then, to look at these buffer solutions, what we're going to do then is we're going to talk about this common ion effect. Okay, we're going to look at the equilibrium of involved in this buffer solution first. Okay? And so what I'd like us to do then is let's consider then what happens if we have this generic acid here. Okay, so we have a generic acid right here. Okay, it's the HA acid. Okay, so the generic acid, remember, this generic acid, when it dissociates, okay, and and it has to be weak acid. And that's the other thing. I'm sorry. When we make a buffer solution, it's always going to be a weak acid and its conjugate base, or a weak base and its conjugate acid. The main reason for that is strong acids and weak acids, they dissociate almost 100%. Okay? And so we won't have any reverse process here. Okay, so with that said, then we have then the conjugate base forming right here. Okay, so if you take a look at this here, we can introduce the anion here. Okay, we can introduce this anion into the solution. So if you can imagine then taking a beaker, for example. Let's go and do this. Let's take an example here. We take a beaker, okay, and into this beaker, okay, we're going to pour some of our generic acid. So inside this beaker here, okay, we're going to add in our generic acid. And we add that in. When we add that in, we're going to have then hydrogen ions floating around. We're going to have the anions floating around. But because this is a strong, weak acid, we're going to have a lot more of the undissociated acid floating around as well. So that's what we have with the initial solution. What we can do then is we can add to this particular solution, we can add in the sodium. Whoops, sorry. I'm going to do this. We can add in the sodium ion that's attached to the anion. Okay. Okay. So we have then this compound, and we go ahead and we add this into the solution. When we add that into the solution, what we're going to do then is we're going to introduce more of the anion. Okay, we're going to add more of the anion. The sodium ion, remember, doesn't do anything, so we're going to add the sodium ion in there as well. So the sodium ion's floating around, but the sodium ion doesn't do anything. So we have then, when we add in this base here, we are making a solution then of both the undissociated acid and its conjugate base. Okay, and that's what a buffer solution is. So the buffer solution then is a solution in which you have, in this particular case then, okay, the undissociated acid. Whoops, sorry. This really quickly. We have the undissociated acid, okay, and its conjugate base. So in doing this here, okay, and sorry, okay, in adding this together here, we have then this floating around and this floating around. And this is how we write a buffer solution. Okay, we put a backslash here, the acid, undissociated acid, and the base here. And so this is what we refer to as a buffer solution. However, if you consider this then, if you're going to add sodium A into this here, what do you think would happen? Imagine what would happen to this equilibrium here if we added more of the anion, if we added more of the conjugate base. Do you see then that the equilibrium is going to shift towards the left? And if it does shift towards the left, then we're going to reduce the amount of hydrogen ion that forms as well. And so as we do that, so as we add in more of the anion here, we're going to shift the equilibrium back towards the left. Okay, and therefore the hydrogen ion concentration goes down. So as the hydrogen ion concentration decreases, okay, the pH then will increase, which means then we have then the acidity will go down. Okay. So we have a solution that's less acidic. And that's what happens when we add in this common, this is what we refer to as a common ion. So there's a common ion that's shared between the acid and the salt that we add in there. Okay, so this is the acid, okay, and this is a salt. So these are two different compounds, but they share this common ion, the A minus. And as a result then, this salt then is going to affect the equilibrium of the acid itself. Okay, so when you add in the acid here all by itself, it's going to be at a certain pH. But you add in this common ion right here, equilibrium, using the Chartier principle, it's going to shift towards the left. That's going to change the pH. It's going to increase the pH, which is going to then reduce the acidity, which means then we have a drop in the acidity. Or the other way you can think about it then is that the basicity is going to go up. Okay, and so that's what we see with the common ion effect. Okay, so with the common ion effect, let me go ahead and save this really quickly here for you. Okay, so with the common ion effect, what we see happening then is that we will affect the equilibrium of the acid itself. And that's the first thing we're going to notice in this. Okay? And so as we see this here, let me go ahead and advance this here. And that's what we see. It's going to shift the equilibrium position because you're introducing in an ion that is already part of the equilibrium. The equilibrium will change because of that common ion. And equilibrium here is going to be important because remember, when we dealt with equilibrium back in chapter 4, we dealt with the ice. We had to make sure then that we dealt with we used our ice tables in order to calculate for the shift. You got to make sure you keep that in mind because with the equilibrium problems that we're going to do now, okay, we are not only going to do the ice table, but we also have to throw into that um, um, uh, stoichiometry as well. So you got to make sure you're able to deal with both. Okay? All right. So with that said, then you take an example here. Okay. So if we take hydrofluoric acid here, this is the equilibrium that we expect. Obviously, this is not going to be exactly equal. Hydrofluoric acid is a weak acid. So we would expect then that the equilibrium should favor the left-hand side. Ka is going to be relatively small. We saw that Ka for HF was around 10 to the minus 4 in the previous chapter. Okay? Now, if we take and we add this salt here that has the fluoride. So sodium fluoride in water, when you dissolve it in water, will form then sodium ions and fluoride ions. The common ion between these two these two processes here is the fluoride ion. You have the fluoride ion that is in common that both of these solutions have in common. So if you have a sodium fluoride solution and you have a sodium hydrofluoric acid solution, the common ion here is the fluoride ion. Okay, so there's the common ion. Okay, and so what will this common ion do? Well, let's consider what we have here. Okay, so let's make sure we understand them. Fluoride is the common ion that exists between both of these solutions. Okay, so we have two solutions here. You have a hydrofluoric acid solution. You have a sodium fluoride solution. What would happen then if we add the sodium fluoride into the hydrofluoric acid solution? Okay, so let's consider what would happen here. Okay, so we add that in. We will obviously increase the amount of fluoride ions. So we're adding in the sodium, remember, doesn't do anything over here. Okay, the sodium doesn't do anything. It's gonna, but the fluoride ion will affect because we have the common ion here. So with that said, then equilibrium is going to shift away from the right-hand side. Okay, and so therefore you're going to have less hydrogen ions present. Okay, and we can talk about this again. If there's if the concentration of hydrogen ion goes down, okay, you have less hydrogen ions floating around. You would expect then we have a less acidic solution. It's going to be more basic, and the pH is going to go up. Okay? And so that's what you want to make sure you keep in mind. Okay? And so let me just make sure I make sure that you understand what I mean by that, because I think this is an issue that many students have had in the past, and they're not quite sure what that means. Okay? All right, so let's use some numbers here, and let's just take some numbers here to help us kind of see what's going on here. Okay? So I had said then that if the hydrogen ion concentration goes down, okay, and let's just arbitrarily pick some numbers here. Okay, so if the hydrogen ion concentration goes down, let's go ahead and I'm going to give you some numbers here in order for you to kind of understand what that means here. So we start out with a 1 molar solution of hydrogen ions. Okay, let's go and consider then a 0.1 molar solution of hydrogen ions, and then a 0.01 molar solution of hydrogen ions. All right, so if we were to calculate for the pH of each of these solutions here, let's go and do that really quickly. Okay, so the hydrogen ion concentration is decreasing here. So let's make sure we understand what we have here. We have a decrease in hydrogen ion, decrease in hydrogen ions as we go down. So hydrogen ion concentration drops. Okay, as we go down this this row here, column here, a hydrogen ion decreases. So we decrease as we go down. Okay. All right. So we do the quick math here to calculate for the pH of the solution. So the pH here is going to be, and I'm going to hopefully you can do this. Okay. The pH here is going to be 0. The pH here is going to be 1, and the pH here is going to be 2. So if you notice here, as the hydrogen ion concentration goes down, what do we know? What do we see happening with the pH? The pH goes up. So as the hydrogen ion concentration goes down, the pH goes up. Okay, so that's what I've been trying to tell you. If we have a drop in pH here, we have an increase in the pH. If the pH increases, that means then we're going from a more acidic solution to a less acidic solution. So we have a lower acidity on this side. Okay, and we have a greater acidity on this side. Okay, so acidity is going to drop. So as we see a decrease in hydrogen ion, we're going to see a decrease in the acidity, but an increase in the pH. However, with that said, as the acidity decreases, we have a greater basicity on this end. So the basicity increases, whereas on this side there, we have a low basicity, okay, lower basicity. So you got to kind of keep track of all of what's going on here, you guys, because we will be referencing this, and the exam, the AP exam plays around with this quite a bit. Okay, so hydrogen ion concentration. If the hydrogen ion goes down, if the amount of hydrogen ions drops, okay, the pH goes up. As the pH goes up, then we have a lower acidity. We have a less acidic solution, but it's more basic. Okay? The less the less acidic a solution is, the more basic it will be. The more basic the solution is, the less acid it will be. Okay, so you got to make sure you keep that in mind as we move forward with this. Okay, so I hope that helps. Okay, so low pH then means then we have an acid solution. High pH means then we have a basic solution. Okay, so as we add in this common ion, okay, as we add in this common ion, we are decreasing the amount of hydrogen ions because we're shifting the we're shifting the equilibrium back to the left. We're going to have less hydrogen ions, okay, and as a result, the pH is going to go up, and the acidity, as a result of that, then we have a less acidic solution. Okay? So make sure you keep that in mind as we go through this. And again, I only point this out. I'm emphasizing this point. I'm hammering on this point early because this is something you really got to keep track of. Okay? All right, let's take a look at another example here. Okay, so we have this solution right here. We have a solution of hydrocyanic acid. So let's focus on that. So our first solution here is going to be a solution of hydrocyanic acid. It dissolves in water, and when it dissolves in water, we have this equilibrium here. So remember, this represents the hydrogen ion right here. So that's your hydrogen ion right there. Okay. So what would happen then if we added in this solution, sodium cyanide? So that means then the equilibrium, or the solution that we're looking at here, when we add it to water, it is going to be then the sodium ions, okay, floating around in water, and the cyanide ion floating around in water. Common ion, the cyanide ion. And if we add sodium cyanide to hydrocyanic acid, we expect then that the pH here, first of all, the hydrogen ion concentration, okay, if we add that in, it's going to drop. And again, I'm going to repeat this for you. If the hydrogen ion concentration is going to drop, we're going to see then the pH is going to go up as a result of adding more the cyanide. If the pH goes up, then we have the acidity is going to go down, and it's going to be more of a basic solution. Now that doesn't mean it's going to be a basic solution. It's just going to be, it's going to have a more base characteristic. I mean, the pH is going to go up. You're going to have more hydroxides floating around, for example, or and this is going to be key, if you have less hydrogen, if you have less hydrogen ions floating around, it's going to be a more basic solution than what we had without the cyanide ion. Okay? All right. So with that said, make sure you keep that in mind. And again, this is something that's going to come up again, and I will point this out again as we go through this particular chapter here. Okay. So it's going to shift the equilibrium to the left, and we see then that we're going to end up with a less acidic solution than if we had hydrocyanic acid on. The pH is going to change. The pH is going to change as a result of that common ion. Okay? All right, let's take a look at an example problem here, and let's calculate this. Let's calculate, and let's see how the pH changes. Let's see how the hydrogen ion concentration changes as well. Okay, so let's go ahead and take a look at this. Let's take a look at an example here. I'm sorry, before we do, let's take a look at an example of a base. Okay, what happens if we have a base solution and we add a common ion there? Okay, so here we have ammonia. So this is the first reaction here. Okay, so we have ammonia here. Okay, and let's say then if we have ammonia, and this time we're going to add this particular. Let me go ahead and let's add ammonium chloride. Okay, so let's add a solution of ammonium chloride. Okay, and if we have a solution of ammonium chloride in water, so ammonium chloride, sorry, and we add, sorry guys, erase this really quickly, try that again. Okay, so ammonium chloride in water. Okay, I hope you see what the common ion is here. So again, the equilibrium here, I'm sorry, this is not quite an equilibrium, this is a dissociation. So let me leave this in there, because in the next chapter we're going to talk about equilibrium involving solubility. So let me leave that in there. This is an equilibrium process as well. We're going to have then ammonium ions and chloride ions. Okay? So common ion here now is ammonium. Okay? That's the common ion here. If you add the ammonium chloride in here, it's going to shift the equilibrium back towards the left. Okay, and so in this case, then, if we shift it back towards the left, let's consider what happens here. The hydroxide ion concentration is going to go down. Okay, so if the hydroxide ion concentration goes down, what do we see happening here? We're going to see then that the POH, and this is going to be very similar to what we did with pH. The POH is going to go up. Okay? And if the PaOH is going to go up, I hope then that you can do this in your head. The pH is going to go down. Just take 14 as you increase the POH. You subtract it after 14. The pH, whatever's left over, is going to get less and less. So that means then the basicity of this solution is going to go down, but the acidity is going to go up. Now understand, again, this does not mean that we will have an acidic solution. We can't. As long as the hydroxide's there, we won't have an acidic solution, but we are increasing the acid character of this solution, okay? Because we are reducing the base character of this solution. So this is true for the bases. Okay? So we saw then what happens when we add a common ion for an acid. Here's an example of a common ion where we have a base solution. So we have a base solution of ammonia. When we add in the common ion of ammonium, we reduce the base character of this solution here. That means then we're going to increase the POH and decrease the pH. Okay? So the idea then is that the pH will be affected. Whether you're in an acid solution or a base solution, the pH will be affected by an addition of a common ion. Okay, and that's what we're going to be examining in just a moment, and we're going to talk about the we'll do a calculation to help you see this. Okay, so with that said, then again, if we add ammonium chloride, the pH is going to shift. The common ion here is going to be the ammonium ion. Okay? And with that said, well, we're going to change the equilibrium. Okay? And so with that said, we have then a less basic solution than if we had ammonium by itself. All right, very good. Let's go ahead then and let's do a quick calculation to get us to see this. Okay? So let's take a look at this. And let's work this one out and let's see how we can approach this. Okay? All right, so the two solutions that we're looking at here, let's go ahead and write these down. The two solutions that we're going to examine here is the hydrofluoric solution, hydrofluoric acid solution. So this is going to be HF. And again, I'm going to leave out the water just for the sake of time here. Okay? And then we're going to have hydrogen ions and the fluoride ions. To this solution here, we're going to add the sodium fluoride, okay, which will dissociate, okay, to give us sodium ions, okay, and the fluoride ion. So we have our common ion right there. Okay. Now, back, and this is referencing what we did. Back in chapter 14, we did this, and we saw that for a 1 molar solution. So if we take a look at a 1 molar solution of the sodium fluoride, so if we had a 1 molar solution of sodium fluoride, remember we did this. We saw then that we had a. Let me go ahead and give this to you really quickly. We saw then that we had a. Sorry, guys. Let me go ahead. The pH here for 1 molar solution of hydrofluoric acid, the pH was 1.57. Okay, and we had a 2.7% dissociation. Okay. That means that we had a 2.7% dissociation when we had a 1 molar solution of hydrofluoric acid. And these are some of the values that you need to make sure you keep in mind. Okay, so that's what we have, and what we're going to do is we're going to compare. We're going to compare what happens to the pH and the percent dissociation when we add to this 1 molar solution. We add 1 molar solution of sodium fluoride, and that's what we have right here. So let's go ahead then and let's see what happens. Okay, so if we add in a 1 molar solution of sodium fluoride, let's make sure you understand then that we will have a 1 molar solution of sodium and 1 molar solution of fluoride ions floating around. Okay. So that's what we want to do when we get started with this. So let's go ahead and let's examine then what happens here. So let's go ahead, and the first thing we want to do then is we're looking at this equilibrium here. So we're going to write that down again. So our equilibrium calculation is going to involve this equilibrium here because we want to see what changes, what happens to the pH and the percent dissociation of this. So let's go ahead and write that down. Okay, so we have then hydrofluoric acid, okay, hydrogen ions, okay, and fluoride ions. So again, the reason why we want to do this is we want to see what happens to this equilibrium when we add in fluoride. We're looking at this equilibrium. So the Ka for hydrofluoric acid again was 7.2 times 10 to the minus 4. I'm going to go ahead and I'm going to write that down for you as well. Okay. All right. The ice table then. This is where things change. So when we did this in the previous in the previous chapter, we said that we had a 1 molar solution of hydrofluoric acid, and we still do. Okay? And at the very beginning, we have no hydrogen ions because we're saying that the dissociation doesn't occur yet. Okay. However, and then we said then that there's no fluoride ions because this dissociation has not occurred yet, and so we would not have any of the fluoride ions either. Okay. The key difference here now is this. We're saying then that we are adding this amount of fluoride ions before this dissociation starts. So we already have fluoride ions floating around. The way that I can get the folks to see this sometimes is imagine if we had a solution. So what we're going to do is we're going to kind of do it in reverse here. Let's say we had a solution of sodium fluoride. Okay, so we had a solution of sodium fluoride here, okay, and inside this beaker here, we're going to have sodium fluoride floating around. So we have then a sodium fluoride solution. So we have sodium ions floating around and fluoride ions floating around already. To this solution then, what we're going to do then is we add the hydrofluoric acid. Okay, we add the hydrofluoric acid into this solution here, which means then when we add the hydrofluoric acid, then we already have fluoride ions floating around in there, and we have a certain concentration of it. And in this particular case, we have a 1 molar solution of hydrofluoric acid. So this is the big difference here. That is, we don't have 0. It's not 0 here. It's not 0 molar solution of fluoride ions. We actually have now a 1 molar solution of fluoride ions. And that is what we need to keep in mind. Okay, that's the key difference. So the initial concentrations here are given to us. So again, we still don't have hydrogen ions because the hydrogen ion has to come from this dissociation, but we already have fluoride ions floating around. Okay. All right. After that, everything else is pretty straightforward. It's just like what we did in the previous chapter. Okay. And we can solve for it pretty much almost exactly the same way. And again, the only difference then is this right here. Okay. We have now a common ion, and that common ion must be expressed in the initial concentration. So do not forget that, you guys. So when we do this here, please don't forget then that the common ion must be written in here initially. So the amount of the common ion that we have has to be written in there before we worked, whereas before we did not have to include it. Okay. All right. So at this point, then we can go ahead and set up the law of mass action. I'm going to go ahead and just plug it in. It's going to be 7.2 times 10 to the minus 4. It's going to be equal to then x times 1 plus x, okay, all over 1 minus x. Okay, so that's going to be the key difference. So now we have a term in the numerator that has a numerical portion and the unknown variable as well. Okay. All right, so at this point, then we're going to approach solving this in pretty much the same way. Okay, assume the 5% rule at this point. We're going to assume the 5% rule here. So 5% rule, and then we're going to assume that. And if it doesn't work, then we have to go back and obviously we're going to have to use the quadratic equation. But let's go ahead and let's assume the 5% rule first. Okay, so I'm going to leave it up to you to solve for this one. Okay, but if we assume the 5% rule, then x ends up being 7. And you're going to see this, then it's going to end up being 7.2. Hopefully you can see this times 10 to the minus 4. Okay. All right. So x, we ignore the x's, the ones cancel out. So x is going to be 7.2 times 10 to the minus 4. Okay. And that means then the hydrogen ion concentration is also going to be equal to that. Whoops, sorry. So there it is, the hydrogen ion concentration, which is going to be 7.2 times 10 to the minus 4. Now, if you plug it back in and you compare the 5% rule, we're going to see that actually does work. Okay, the 5% rule actually does hold. Okay, the 5% rule does hold, so that we don't have to use the quadratic in this particular problem. So the 5% rule works. Okay. All right. So let's go ahead then. First thing I would like to do then is let's calculate for the pH. Okay, so the pH then of this solution. And I'm running out of time here. So let me go ahead and just give it to you. Okay, the negative log of 7.2 times 10 to the minus 4. We expect the pH to change. Remember, we said then that if you have a common ion, what did we say? And before I give you the answer, and we talked about this, the equilibrium is going to shift down back towards the left. Okay, which means then that the hydrogen ion concentration is going to drop. We already said that. Okay, so let's go ahead and let's look at what we know prior to going into this. Okay, we know then that by adding in this common ion here, okay, we have then, we know then that the hydrogen ion concentration will go down. Okay. We didn't calculate for it here. Well, we don't have that, but what we're going to do then is we're going to say then that we're going to predict then, based on what we know, that the pH is going to go up. If the pH is going to go up, which means then we're going to have an acid, the acidity of the solution is going to go down, and the base character of the solution is going to go up. Let's see if that holds true. Let's see if that holds true in what we've done right here. So this is what we know from Le Chatelier's principle. This is what we predict with that common ion. Okay. All right. So the pH of this solution. Okay, the pH of this solution, then when you plug it in, you get a pH in of 3.14. The pH here is going to be 3.14. And sure enough, our pH went up. We went from 1.57 to 3.14. That is correct. Okay, which means then as we go from we're going from low pH to high pH, the acidity goes down and the basicity goes up. Exactly what we expect to happen. Exactly what we expected to happen right there, and we see it in our answer right here. And you can go ahead and calculate for the hydrogen ion concentration. And actually, I'll give it to you. I'll give it to you. We did this back in chapter 14. The hydrogen ion concentration for this solution here, this original solution, was 2.7 times 10 to the minus 2 molar. And so if you notice here, the pH went up, the hydrogen ion concentration went down. We went from 10 to the minus 2 to 10 to the minus 4. Again, exactly what we expected, applying Le Chatelier's principle. That's exactly what we expected as well. And that part also holds true. Okay. All right. The last piece of information that I wanted to examine, which is somewhat interesting as well. Okay, and so we calculate for the percent dissociation. Percent dissociation, and please make sure if you don't remember it and you're not quite sure how we get this number, come by and see me. We have then a lower percent dissociation. We have 0.77%. And I hope you can see why. Okay, why? Because we're shifting the equilibrium back to the left. And so therefore the dissociation is going to drop down as well. Okay, so it's going to be 0.077 as opposed to 2.7. We have greater dissociation, but when we add the common ion, we're shifting the equilibrium back towards the left-hand side. We expect that to go down as well. We have less hydrogen ions. We have less hydrogen ions. And so we expect the percent dissociation to go down as well. So by adding a common ion to an existing equilibrium, okay, by adding a common ion to an existing equilibrium, we change that equilibrium. We change characteristics of that equilibrium. And that's going to be important as we move forward with this. Please make sure you keep this in mind, because the big picture now that we're trying to examine, using what we know right now, examine how the properties of buffers and how buffers are how buffers then work when you add in an acid or a base to a buffer solution. Okay. All right. We've run out of time here, so we will pick up with this on Thursday. So please make sure then you take a look at it, and this is section 15.1. Please take a look at it, and that way then on Thursday when we discuss this, it'll be a little bit better for you. But please stop by I'll be available if you can watch this video early, right after examine. I'll be available till 1 o'clock. 11:30. Come on by. We can talk about the buffer, what this is all about right here. Okay. All right. Very good, folks. If I don't see you tomorrow, I hope to see you. I'll see you on Thursday. Okay. I'll see you later.